It's a pleasure to talk to you. I'm Granger Morgan from Carnegie Mellon in the Department of Engineering and Public Policy, and I want to give a few basic ideas about climate change, starting with 4 key facts. When coal and oil are burned, carbon dioxide is released to the atmosphere. Carbon dioxide is a greenhouse gas that causes the average temperature of the planet to warm, and that warming causes other changes to the Earth's climate. 3, carbon dioxide is not like regular air pollution, things like sulfur dioxide or oxides of nitrogen. Regular pollution only stays in the atmosphere for a few hours or days. Much of the carbon dioxide stays in the atmosphere for 100 years or more. So, once climate has changed, we can't just stop emissions of carbon dioxide and fix the climate change problem. Now, I'm going to talk about 3 things. I'm going to talk about why adding carbon dioxide and other greenhouse gases warms the Earth. Then I'm going to talk about how the climate is changing and some of the impacts that change is causing. And then finally, I'm going to talk a bit about what we can do to reduce climate change and to adapt to the changes that we simply can't prevent. But before that, let's start with a little quiz. What's the average temperature of the Earth? Take a moment, think about it, and write down a number. Now, of course, the poles are cold and the equator is warm, but if you averaged over the entire Earth, the average temperature is about 60 degrees Fahrenheit. So that one's not too hard. What's the average temperature of the moon? This one's much tougher. Obviously, on the side that's in full sunlight, it's very hot. It's actually about 250 degrees Fahrenheit. On the backside, it's really cold. It's about minus 380 degrees Fahrenheit. If I just average those 2 numbers together, I get a number like 64 below. In fact, it's not quite right, but it's close. The average temperature is more like 0, whereas the average temperature of the Earth is 60. So why the big difference? And the atmosphere of the Earth is, of course, what makes the difference. We'll talk more about that in just a moment. But let's do one more of these quizzes. What's the average temperature of Venus? Now, I've already given you a hint. It's the atmosphere that controls the surface temperature, and the atmosphere of Venus is made up almost entirely of carbon dioxide. So the average temperature of Venus turns out to be about 860 degrees Fahrenheit. So hot that if you had lead or solder on the surface of Venus, they would be molten. All right, so now let's figure out why the atmosphere makes such a big difference. So here we have the sun shining on the Earth. About 30% of the energy that comes in is immediately reflected right back out into space. But about 70% of it is absorbed by the atmosphere and the clouds and the ground. And if it just kept getting absorbed, the Earth would heat up and we'd all fry. So to stay in balance, that energy has to be somehow radiated off the top of the atmosphere back into space. And there's where the problem comes, because the atmosphere is transparent invisible light. But it's opaque to heat, because infrared is absorbed by a variety of things like water vapor, carbon dioxide, and other greenhouse gases. So heat energy gets trapped, and the planet warms up. And this is termed the greenhouse effect. Now, for those of you who are a bit more technical, here's a plot that actually shows that. On the top, I've got the emissions from the sun, which are mainly in the visible range. And then, of course, the Earth, like a radiator, emits heat, and the visible light comes in through the atmosphere without any difficulty, but because there's carbon dioxide and water vapor and other gases in the atmosphere, that heat energy can't get back out. And so, as I said, the planet warms up until finally it's gotten warm enough that the same amount of energy in the form of heat is radiated off the top of the atmosphere back into space. Now, of course, more of that energy from the sun comes into the equator than to the poles, and so if there wasn't some mechanism to distribute the energy, we would not have quite as pleasant a planet as we have, but there are 2 mechanisms, and they each carry about as much energy from the equator to the poles. The first is the atmosphere, shown in the upper right here. This is exaggerated vertically because, in fact, of course, the atmosphere is just a little bitty thin shell when viewed in that picture. The other thing is an ocean circulation, often called the ocean conveyor belt, which also moves about half the heat from the equator towards the poles. Now, back in the 1960s, somebody named Dave Keeling at the Scripps Institution of Oceanography started measuring the amount of carbon dioxide in the atmosphere. He did this on the top of a volcano, Mauna Loa, in Hawaii, and he put his instrument there because he wanted clean air off the Pacific. I mean, if he did it just outside his lab, of course, every time a truck or a bus went by, it would measure the CO2. But this was clean air that was measuring sort of the atmospheric background, and he got this sort of record. Now, you can see that there's been steady growth, and actually the line I've drawn there is the expected rise you would see if 57% of the fossil fuel emissions remained in the atmosphere. That is, 57% of the carbon dioxide from burning coal and oil and natural gas stays there. The rest ends up in various other places, much of it in the ocean. We'll come back to that. What's the little wiggles on the curve? Well, this is in the northern hemisphere, and in the northern hemisphere, of course, we got a lot of plants in the summer, and plants take up carbon dioxide, and so that's the summer-winter oscillation. You can see this growing trend in concentration all over the world. Here's a website that NOAA, the National Oceanographic and Atmospheric Administration of the U.S. government, has. And if you click on any of those stars, for example, here's one for Barrow, Alaska, you can see the same sort of record. This is in a northern hemisphere site, so these oscillations are very big. If you clicked on the Antarctic site there, they would be much smaller, but the growth would be the same in both cases. Now, as we humans keep adding carbon dioxide and other greenhouse gases to the atmosphere, the temperature of the Earth has been going up. You've probably seen these basic plots. Here's the temperature record, and you can see that in the last few decades, actually basically since the end of the beginning of the Industrial Revolution and the growth of carbon dioxide in the atmosphere, the temperature has risen. But this is all kind of abstract. So let me try to make it more concrete. Consider the Bruce Mansfield Power Plant. This is a 2,000 megawatt plant that's located on the Ohio River just west of Pittsburgh. A plant this size burns the equivalent of about 230 of these 100-ton hopper cars of coal every day. Now, of course, coal's also got some ash in it, but if coal were pure carbon, that would be the same as taking 130 cars like this, converting it into an invisible gas, carbon dioxide, and releasing it into the atmosphere every day. And hundreds of such plants are operating like that all over the world. So the next time you see one of these big coal trains go by, remember, most of the mass in those big hopper cars is going to be in the atmosphere in a few days. Now, here's one of the points that I made in my opening slide. Carbon dioxide is not like conventional air pollutants. Pollutants like sulfur dioxide or oxides of nitrogen have a residence time in the atmosphere of just a few hours or days. If you stabilize emissions, then the concentration in the atmosphere stabilizes, and for that matter, if you stop emissions in a few days, it's all gone. That's not true of carbon dioxide. If you stabilize emissions of carbon dioxide, because carbon dioxide lives in the atmosphere for a very long time, concentrations just keep going up and up. And so when CO2 is emitted, it lasts from the atmosphere for about 100 years. If you want to stabilize concentrations in the atmosphere, you need to reduce emissions by something like 80% or more, maybe even as much as 90%. Here's a useful analogy. Think of a bathtub with a very large faucet and a very small drain. That small drain is the rate at which CO2 leaves the atmosphere, and that big faucet is the rate at which we're putting it in. And unless you really close down on that faucet, the concentration or the level of the bathtub is just going to go up and up. So that completes the first part. Now let's talk about how climate is changing and some of the impacts that it's causing. And I've got 4 pictures here that will sort of lay the groundwork. Well, then we'll go on and talk in greater detail. The first picture shows the amount of spring snow cover every year from the 1920s and 30s up to the present. And you can see in recent decades, spring snow cover has been falling off. Similarly, Arctic ice extent has been falling. That is, the amount of the Arctic Ocean that's covered with ice. We'll come back and look at several of these in greater detail. The next plot shows the temperature of the surface layers of the ocean, and the last shows sea level. And we'll talk about why sea level is going up. Let's start with that one. As water warms, it expands. So both for this reason and also because of melting glaciers, global warming will produce sea level rise. The recent studies by the IPCC, which is the international organization that studies climate change, have not included very much ice loss from things like the Greenland ice cap. But if you lost, for example, all of the Greenland ice cap, that would raise sea levels by about 23 feet. Suppose, just for the sake of seeing what that means, that we lost half of Greenland, 11 and a half feet or something like that. So here is Florida and the Gulf Coast, and here it is with 11 and a half feet of sea level rise. All right, let's now also look at Manhattan. Here's Manhattan, and here it is with 11 and a half feet of sea level rise, and you can see, for example, that a number of airports and other things are going underwater. Now, of course, in New York, we'd probably build dikes, but still, you don't want to put a population of millions of people below sea level if you can help it. Warming will be greatest at the poles. The extent of summer polar ice is already decreasing. And some now argue that the Arctic may be free of ice in the summertime in just a few decades. That, of course, does a job on the habitat for things like polar bears and sea lions, but it also means that the Arctic Ocean might be open for shipping. On the left top here is a plot of the extent of sea ice coverage in August over the recent years. And if you look, we're right on track for what the models say are going to happen. The plot on the left just shows year to year how things have been gradually dropping. Now, lest you think this is only the concern of climate scientists and environmentalists, here's a report done by the Office of Naval Research called Naval Operations in an Ice-Free Arctic. This was done during the first Bush administration. Here's a much more recent report done by the National Academies of Science for the U.S. Navy, again looking at naval force issues in the Arctic. Clearly, if you took all the ice out of the Arctic Ocean, the Navy would be very concerned, and the Navy is very seriously looking at the implications of this. The Arctic is vulnerable, but so too are small island states and coastal estuaries. For example, it could be that many islands will simply disappear as you get sea level rise. Mangroves are another threatened ecosystem. Mangroves are sort of funny-looking places, but they're very important as breeding grounds for many oceanic species. Alpine meadows may begin to disappear because if I have a mountain with various climate zones up the mountain, if I warm the planet, the alpine meadow may get pushed off the top of the mountain. And lastly, coral reefs. Let me explain a little more about coral reefs. Coral reefs are threatened for two reasons. They don't like heat, but they also don't like acidic water. Much of the CO2 that we put into the atmosphere ultimately ends up in the oceans. You saw this red curve before. That's the Keeling curve from Mauna Loa. What you maybe never have seen is the blue curve, which is the acidity of the ocean as measured in pH. And today the oceans are about 30% more acidic than they were before the Industrial Revolution. So here's a plot or a set of pictures from a recent piece in Science magazine. The left-hand image shows a normal coral reef with today's concentrations and maybe about a 1 degree rise in temperature. If the concentrations of carbon dioxide go up to 450 or 500 parts per million, that's about a 2 degree warming. You could lose a lot of coral, and at above 500, that is 3 degrees or more, basically a lot of coral reefs are going to be gone. And at the moment, we're basically on a trajectory that will get us to that 3 degrees or more by sometime late this century or early next century. It will also mean a dramatic decrease in the ability of organisms to make shells. And you know about shellfish, of course, but it also turns out that very small organisms like pteropods or sea butterflies, which make very thin shells, are the bottom of the food chain for things like juvenile salmon. Here's a paper that our center at Carnegie Mellon funded with investigators at Woods Hole Oceanographic Institution that looks at the impact of losing mollusks, that is shellfish, around the coastal Pacific. And it reaches the conclusion that countries with low adaptability at high nutritional dependence on mollusks will be most vulnerable to ocean acidification because they won't be able to get the protein that's currently part of their diet. Drought, extreme events, pests and fires are also important, and I've shown you pictures here of drought. The bottom left picture is pine bark beetle, which used to be killed off when the forest got very cold over the winter, but because the forests aren't quite as cold anymore, the beetles live through. That in turn can give rise to fire and flash flooding. This picture in the lower right corner is actually a picture that I took here in Pittsburgh during a flood in a portion of Washington Boulevard. Now, we can't say that any single event is caused by climate change. However, what scientists have begun to do is to compare the statistics of events like this in the past with events today and going forward. And so what you can say is that these events are becoming more and more likely, and that climate change is almost certainly contributing to at least some of them. There are continental ecosystems that a lot of us hold very dear. I grew up, for example, in central New Hampshire. Central New Hampshire has an ecosystem of white pine, maple, beech, and birch. And if climate change continues as it currently is progressing, those will all be gone to be replaced by yellow pine and oak. And yellow pine and oak look great, but from my point of view, that's not New England. If you lose all of those, this is a picture of my backyard in the house where I grew up. Here is, courtesy of Steve Hamburg, the chief scientist of Environmental Defense Fund, a record of what spruce abundance was in the period from 1700 to 1800 and what it looks like today in New Hampshire, largely disappearing. Now, you might say, what about uncertainty? There's no uncertainty about whether carbon dioxide and other greenhouse gases are warming the planet and changing the climate. Talk about uncertainty about those issues is largely the result of intentional obfuscation by people who have economic or political interests. Now, there is uncertainty about how much greenhouse gas humans are going to add to the atmosphere over the next century, and so that makes modeling what's going to happen difficult. How much additional warming those additions will produce, there's a bit of uncertainty about that, and the details of many changes that will result in climate, weather, and oceans, in natural ecosystems, and in human activities. Those are all somewhat uncertainty. But the bottom line on uncertainty is that there isn't any uncertainty about whether adding CO2 and other greenhouse gases to the atmosphere will warm the planet and change the climate. And if you're interested, here is a really very nice book by Naomi Orskes and Eric Conway that explains how the presence of some uncertainty has been used by folks with short-term economic or political interests or scientific publicity seekers to promote doubt in the minds of members of the general public. Now, here at Carnegie Mellon, over the past 17 years, we've been fortunate to receive 3 large center grants on climate-related decision-making. We won these through national competitions. The present center is called the Center for Climate and Energy Decision Making, and the central focus of much of our work has been on characterizing and treating uncertainty. These are anchored at Carnegie Mellon, but as the map shows, we have a variety of collaborating institutions around the world. This brings me to the final thing I want to talk about, which is what can we do to reduce climate change and to adapt to the changes we can't prevent. So here are three options to limit climate change. We can reduce emissions of greenhouse gases, basically by changing the energy system and other things. We can remove CO2 from the atmosphere. That's not easy and it'll be expensive. We'll talk a bit about that. Or we could increase the planetary albedo, that is the amount of sunlight that we reflect back into space, and I'll say a word or two about that at the end. So how are we doing on decarbonizing the world's energy systems? International negotiations among 180 nations are all well and good, but what we really need is serious reductions by just a small number of countries. And you can see from this pie chart that China and the US together make up almost half of all CO2 emissions. If we could lump them together there, the EU, the European nations, would be the next in line. I wrote a piece in Science magazine about 15 years ago called Managing Carbon from the Bottom Up, which said international negotiations are great, but what's going to really happen is, if we manage to get serious about this, is that first one and then another country or region will get serious, and then we'll figure out how to negotiate and merge these regimes. So let's look at the recent agreement between the US and China. My view is that this is very important because this gets us about half the emissions seriously talking about how to reduce. And this may involve some incremental muddling along, but for the first time, it gets the two nations really into serious discussions. Chinese emissions are going to peak at 2030, and the Chinese have committed that they will not grow them after that. And the Environmental Defense Fund reports that at present, China has carbon dioxide trading programs, that is, a price on carbon and limitations in 5 cities, in 2 provinces that cover more than 2,000 sources, 16% of all the greenhouse gas emissions in China. Now, I said there were 3 options. Let's start by looking at the one reducing emissions of greenhouse gases. And since time is short, in this part I'm just going to focus on CO2 emissions from electricity, but obviously automobiles and trucks and cars and airplanes and home heating and factories all produce carbon dioxide. But electricity is a major issue, and so we'll walk through that one. Despite the growing interest in renewables and low carbon energy, the world still makes most of its electricity from coal, natural gas, and other fossil fuels. Now, this particular slide's about 10 years old, but it hasn't changed much. You can see that little narrow green slice, and here's the US just last year. About 40% from coal, about 30% from natural gas, 20% from nuclear, and renewables, you can see together, make up about 7%. Solar is only less than 0.5%, wind about 4.5%. Now, granted, wind is growing and solar is growing quickly, but it has a very long way to go, and we'll talk a bit more about that in a moment. I've listed down the right-hand side here a whole bunch of things we could do, and I want to quickly walk you through each and give you some sense of the role they might play, starting with conservation and efficiency. The plot on the top is a very interesting plot. The very top line is the size of refrigerators over time. The next line down is the amount of electricity refrigerators use over time, and the bottom line is the cost of refrigerators. And what you see is that beginning back in the 60s and 70s, first California and then the United States started imposing energy efficiency standards on refrigerators. Today, refrigerators are bigger, cheaper, and use dramatically less energy than they did several decades ago. That same sort of pattern could be repeated with a number of other major appliances. Lighting is another area where we've made enormous progress. You all know about compact fluorescence, but the new solid-state LED lights are even more efficient. And the plot at the bottom is interesting because it shows U.S. electricity consumption over time. It was sort of growing exponentially until the 70s, and it's been linear since then. But that green plot is Vermont. And this is happening because Vermont is one of several states that has a program, in this case called Efficiency Vermont, which skims a very small amount of money off each electricity bills and then uses it to promote efficient use of electricity across the state. The next thing I want to say a word or two about is fuel switching and distributed generation with combined heat and power. So we're already seeing, for economic reasons, a lot of switch from coal to natural gas. And it turns out that if you burn natural gas, that releases about half as much carbon dioxide per unit energy produced as burning coal. And so conventional economic forces, cheap gas, are pushing some of that switch. But the other thing that's important is that we make much of our electricity out very remote from the load centers in large power plants, where a lot of the energy gets wasted by sending it up as through cooling towers of the sort you see there in the bottom right. On the other hand, if you could make some of your electricity locally near the sources where it's used, you don't have to waste that energy. You could use it to heat water, to heat space, and for that matter, if you got heat with a bit of fancy engineering, you can also make chilled things. And so combined heat, distributed generation with combined heat and power holds the potential to dramatically improve the efficiency with which we use the energy we've got. Nuclear is another issue. As the French have clearly shown, despite its various problems, nuclear power is capable of serving a nation's electricity needs without producing any CO2. About 88% of the electricity generated in France is generated in 58 nuclear plants at 19 different sites. And the issues include costs and public acceptance, safety, risk of nuclear proliferation, and waste management. But nuclear is another part of the portfolio that should not be taken off the table. Wind can play an important role, but as the fraction of installed capacity grows, dealing with intermittency becomes a major problem. Now, this very squiggly here is a full year of output from a wind farm. And most wind farms look like this. And if you're trying to run a power system and you got, power that's coming out like that, it's really hard. Now, in the places like the Northwest, where the Bonneville system has lots of hydro projects, you may be able to fill in with hydropower when the wind stops blowing, but dealing with intermittency is a major problem. If you're interested in this, at Carnegie Mellon, we had a big project a few years ago called the RenewElect project, which explored a whole range of issues of integrating variable and intermittent renewables into power systems, and you can find a lot of the details on the website. You might ask, can't you just smooth things out by connecting a bunch of wind farms together? And the answer is, yeah, you can do some of that. But after you've connected a handful of them together, you don't get much improvement. Now, here's all the wind farms in Texas over the course of a year. The nameplate capacity is that solid line up above, and so you can see the capacity factor, that is the amount of electricity on average produced, is only about 34% of the nameplate. Let's ignore the slide at the top since time is short and just look at the one at the bottom. The figure shows that the amount of reduction in variability achieved as you connect more and more wind farms together, that basically after you've connected 4 or 5 of them together, you don't get much more reduction in variability. And so that means that you got to find other ways to deal with variability. The other variable source, of course, is solar. And while large utility scale solar is getting more cost effective, without subsidies, rooftop solar is still not at what is called socket parity. That is, the price of electricity from your roof is at or below the price of the plug coming out of the wall. This plot here by one of my doctoral students shows that nowhere in the U.S. is the net present value of rooftop without subsidies. Now, we massively subsidize rooftop solar, and so a lot of it's being installed. And there's a learning curve. Things are getting cheaper, but we still have quite a ways to go. Next are geothermal and biomass. These are both interesting, but they're both modest quantities available. Next is coal or gas with carbon capture and deep geologic sequestration. I want to spend a moment or two on this. If I have a coal plant or a gas plant, at the moment the way it runs, I burn either of these and then CO2 goes up the stack. But if I could capture that CO2 and not let it go up the stack, then I could put it away deep underground and not emit it to the atmosphere. And here are 3 technologies that could do that. The first is put a scrubber on the back end. Problem, of course, is that since the atmosphere is mainly made up of nitrogen, most of the exhaust that comes out of a coal plant is nitrogen, with only a bit of carbon dioxide from burning the coal. And so scrubbing it out is very expensive because it's quite dilute. Another thing I could do is separate it before I burn, and then lastly I could burn in pure oxygen, in which case I don't have all that nitrogen. I could just have a fairly concentrated stream of carbon dioxide. And so all of these technologies are available today at commercial scale. The problem is that we're still trying to figure out how to find the resources to put them together at large scale, because at the moment there's no economic incentive for a utility to do this. There's no limit on the amount of CO2 one can emit to the atmosphere. Now, this technology is not pie in the sky. Indeed, we have 2 IGCC plants, integrated gasification combined cycle plants, now operating in the U.S. We have another capture plant under construction right now. We have a number of different facilities around the world that are capturing and putting CO2 a kilometer or more underground in appropriate rock formations. And once the CO2 has been captured and injected into suitable geologic formations, it basically will stay there forever. The plot at the lower left shows you the parts of the world where there are good formations to do this, and you can see the United States in particular is very favorably positioned to adopt this technology. For many years, my colleague Ed Rubin and his students have been building models of conventional and advanced fossil power plants, and a few years ago we then concluded that while the technology for CCS, carbon capture and sequestration, is really important, so too is developing a regulatory regime that assures that it's going to be done in a manner that's safe, environmentally sound, affordable, and compatible with evolving international carbon control regimes. Now, we are at the moment making progress state by state, but the point of this project was to try to develop a national approach that was more unified. And if you're interested, you can see this book, Carbon Capture and Sequestration, that we published through RFF Press. One picture out of that book that's important. We think about learning curves as, I build the first one, it's very expensive. I build the next one, it gets a little cheaper, and then finally after I build a lot of them, it's gotten quite cheap. These 2 plots show you curves for both sulfur dioxide scrubbers and nitrogen scrubbers, and you'll see they don't just start high and go down. They start low, and then you say, oh, that one didn't work, let's try a little different design. Oh, that one hasn't worked either. And finally you get one that works, and then you come down. We got to get over that hump, and at the moment we're not moving fast enough to do that. Achieving an order of magnitude reduction, that is a 90% or so reduction in CO2 emissions, will take everything we've got. There basically aren't any silver bullets. And here, for example, is a result from a recent study by the Electric Power Research Institute, but there are dozens and dozens of studies like this that show the only reasonable, cost-effective way to decarbonize the system is to use a portfolio. Now, I want to just ask the question, how fast could we decarbonize just the electricity system? So here again is a plot that shows the growth of electricity over time. Up until the 70s, it was growing exponentially. That's this curving thing. And then it's been linear since. And then the last few years, it's flattened out, in part because of efficiency, in part because of economic limitations. Each one of those steps in that plot are the same as 36 times as many wind farms in West Texas, which has probably got more wind farms than anywhere else in the country, or 130 of the newest nuclear power plants like the AP1000, or 60 large coal plants. So those are big steps. So here's the same plot, and of course not all the electricity we produce makes carbon dioxide, and so if I start with only the part that makes carbon dioxide, and I ask how rapidly have we been growing, suppose I could replace carbon-intensive plants with carbon-free plants at about that same slope. Then that says I could decarbonize the electricity system in perhaps 40 years. If you want to do it faster, you'll have to replace faster. If you want to do it slower, well, in 60 years, you could take a slightly more leisurely approach. If you're interested in learning more about all of the things that I've talked about up until now, The IPCC, the Intergovernmental Panel on Climate Change, does regular reviews every few years. This is the summary for policymakers. You can find it on the web, and it's easy to read. You might find it interesting. So I want to talk about two final things. First, I said adapting is going to be important. There's simply no way that we're going to avoid some significant change, and the things we can do to adapt involve things like moving crops further north. I mean, the grain belt is probably going to move up into Canada, move coastal settlements to higher ground, and in some cases maybe build dikes and seawalls, although that's hazardous. Build more resilient infrastructure and make it easier to recover after damages from extreme events. Put in place strategies to protect people from extreme events such as heat waves. For example, making sure that there are large public air-conditioned spaces where people can go when you have an extended heat wave, appropriate warning for floods, and many, many more. The last things I want to talk about are these two ideas. First, of removing carbon dioxide from the atmosphere, and second, of increasing the amount of sunlight we reflect back to space. So to warm the planet, add carbon dioxide or other greenhouse gases. That's the figure we saw at the beginning. To cool the planet, I can do one of two things. I can remove carbon dioxide so it's easier for the heat to get out, or I can add something to increase the amount of scattered sunlight and so that the planet doesn't get quite so hot. The first is called carbon dioxide removal, or CDR. The second is called SRM, for solar radiation management. And there have been two recent reports by the national academies that address these issues. They're available online if you're interested. Carbon dioxide removal options are slow. They're either expensive or they don't scale. That is, you maybe work fine in small scale, but they don't work well when you try to scale them up. The best ones do not introduce new kinds of environmental risks, but some of them do. And they do have the advantage that they address the root cause of the problem, which is too much carbon dioxide in the atmosphere. So here's 6 examples of things one might do. The first involves afforestation or reforestation, that is planting trees. And this will capture CO2, but of course, in a fairly limited way. It's not going to solve the climate problem. The next is no-till agriculture, that is, not letting the carbon dioxide in the soil get into the atmosphere. This too is important, but only probably in the short term as a strategy to get started. Biomass fuels have the advantage that, biomass takes CO2 out of the atmosphere into trees or plants, and then you burn it and the CO2 goes back to the atmosphere, but you're not adding it. You're not digging up old carbon from underground and putting it into the atmosphere. People talk about ocean fertilization, the idea of adding iron or other nutrients to the surface layers of the ocean so that the small organisms there might pick up the CO2 and then might sink to the bottom. It's not really clear that's going to work. There have been some experimental studies. And you could try to do some things that enhance natural weathering. Natural weathering over millennia does take some CO2 out of the atmosphere, and you might find ways to speed that process up. Lastly, there are a number of folks who are working very actively on trying to find strategies to build technology that'll scrub CO2 out of the atmosphere. You can do it today. The problem is it's very expensive because the amount of CO2 in the atmosphere is, in percentage terms, very low. But these technologies are making progress and probably will turn out to be possible for several $100s a ton of carbon dioxide to scrub it from the atmosphere. Here are some strategies that might be used for solar radiation management. That is, the idea of reflecting more sunlight back into space. You could add small reflecting particles in the stratosphere. You could add more clouds. You could put various things out in space. Or you could change large portions of the surface of the planet. Adding fine particles to the stratosphere is probably the most practical of these. And so I'm going to talk in a bit more about that in a minute. But adding some surface clouds might help. These are ship tracks in the upper left picture. There are a lot of sort of wild ideas about putting things out in space, but these are going to be incredibly expensive. And, changing the reflectivity of the surface may help a bit, but it's a very local impact. There's no way you're going to solve the problem on a global scale by doing this. So of these three options, reflecting particles is probably the best, and so let me say another word or two about them. Here's a piece that a couple of colleagues and I published in the journal Nature a few years ago, and that little box says solar radiation management has three essential characteristics. It's cheap, it's fast, and it's imperfect. So cheap means that you could probably do it for just a few % of the cost of reducing global CO2 emissions. In other words, it's going to be very tempting as climate change begins to become serious and people get more and more concerned about it. Probably just a few % of the cost of reducing global CO2 emissions. And it could probably be implemented in months or years because big volcanic eruptions, which put a lot of fine particles into the stratosphere, have been shown to lower temperatures of the globe in just a few months. And here's the kicker. Once you get it started, if it was stopped, temperatures would rise very quickly. That would really do a job on ecosystems. It does nothing about ocean acidification, and it could be done unilaterally. That is, a single major nation might decide, oh, our problems are getting serious, we're just going to do this, to heck with the rest of you guys. So here's a plot, for example, that shows the temperature of the planet after the Mount Pinatubo eruption of some years ago, and you can see there's about a ½ degree reduction in planetary temperature as a result of that. So this is not theory. I mean, we know it could work, but what are some of the other side effects? The impacts aren't going to be uniform. Some places will change more than others. Precipitation patterns will certainly shift. Changes in terrestrial ecosystems due to higher carbon dioxide changes will result, and there'll be changes in precipitation patterns. There'll be continued and growing impacts on the oceans as they take up more and more CO2 and become more acidified. And particles in the stratosphere can provide reactive surfaces that might contribute to more rapid destruction of the ozone layer. On the other hand, we think that this is probably an issue that deserves some study, because if we ever got into an emergency, we might need to use a little bit of SRM as a stopgap. So here's a paper that a couple of us published through the International Risk Governance Council, and a couple of recent pieces that I've written arguing for how we should do research and what the management issues that need to go along with doing that. Now, if we're tempted to do SRM, we need to be really careful, because we've only got one planet. So let me finish up where I started with 4 key facts. 1, when coal and oil are burned, carbon dioxide is released to the atmosphere. 2, carbon dioxide is a greenhouse gas that causes the average temperature of the planet to warm, and that warming causes other changes to the Earth's climate. 3, carbon dioxide is not like regular air pollution. Regular air pollution only stays in the atmosphere for a few hours or days, so if I get a problem with air pollution, I can stop emitting and the problem will go away. Much of the carbon dioxide stays in the atmosphere for 100 years or more. So once climate has changed, we can't just stop emissions of carbon dioxide and fix the problem. We need to stop emissions now in order to not get to the point that we've got so much in the atmosphere that we're causing serious problems. And with that, I will say thank you, and I want to thank also my many colleagues, the National Science Foundation and others who've supported a lot of the work that I've talked about.